magical place. What if we thought about our sister, this world known as Venus? If you were out last night and you looked in the sky, the brightest thing other than the moon was Venus. And she has a story to tell us that many of us think is critical to understanding ourselves and exoplanets that may be in different states that we can now study with great space telescopes like the James Webb. We may be able to see Venuses that weren't like the Venus we have next door, which is pretty tough. So I'm going to take you on a tour of what we're doing at NASA to bring us all, humanity, back to Venus. It's an open science tour, so get involved, folks, because we're going back. Let's see if I can do this right. So let me remind you, in 1978, the last time the United States went into the atmosphere of Venus. It's the biggest atmosphere around a rocky planet we've got. It was really cloaked in mystery, volcanoes, swamps, lots of things that we knew weren't really the case, but they were surprising. Massive CO2 atmosphere, super hot at the surface, 950 Fahrenheit, pressure equivalent to 900 meters in the ocean. How many of you have been down in a sub? Okay, well, we're going back now with the 21st century technology inspired by the science of NASA for the Earth and great artists like Leonardo da Vinci. So we're going back to Venus. People say, why? Why have we waited so long? Venus is tough. We have some great women and men engineering at NASA, in the community, but when you have to get to a planet where the environments change from minus 50 at 0.1 bars to 450 at 95 bars in an hour, it's pretty tough. I mean, it's really a magical mystery tour. So we're going back to Venus with 3 missions, 2 by NASA, 1 by ESA, and others by commercial companies to get to see what this planet may be telling us. So this is the Venus problem. We think this is the Venus of 2 or 3 billion years ago. Look familiar? Well, we think that's the case based on very limited data. We have less data for Venus than we have for Pluto. Everyone remember Pluto? She's a great little dwarf world. So here's our sister that we forgot, apparently, and this is what she may have done. Talk about climate change. How does the planet go, and also de-spin, from a state that looks Earth-like to a state that's today? That state is a world where there's almost no water vapor, massive carbon dioxide. Near the surface, the carbon dioxide is not a gas. It's a supercritical fluid, only 11 times less dense than water. Think about that. So we're going to go back to Venus to solve this. I got to do it this way. Sorry, to solve this problem, because Venus also looks a little bit like Earth. You saw Jack show the beautiful volcanoes of various places. This is the big kahuna on Venus, known as Mont Mons. Mont Mons rises 8 kilometers from the plains of Venus, 400 kilometers across. It's bigger than the Hawaiian volcanic system that we know and love in the Pacific. Here she is. And there are thousands of volcanoes, not this big, on Venus. We think they're erupting, but we haven't seen that evidence. So Venus is a planet that went and looks like Earth, but went into a different state. So what we're going to do is address this question. Why, in the name of Pete or anyone, isn't Venus more like Earth? If she may have started this way, at least a steamy early Venus, why is she like this in a period of time that may have only been 1 billion years? What happened? We don't want that to happen to Earth. She may be telling us something, and we may be able to see exovenuses that looked in between with the great power of the James Webbs and others. So we have a mission that was selected, named for Leonardo. Now, who doesn't love Leonardo? I just ask. People remember 500 years ago, he painted things. He also was a scientist, artist, many things. So our mission is going to go to where no one's gone since the 1970s, to the deep atmosphere. And we're going to bring with us the tools of the trade that we used to study Earth, Mars, Titan, other worlds. And we're going to go there ourselves, take the plunge. And the Da Vinci mission was selected in one of NASA's competed programs, and the core of the mission is a flying rover. Doesn't look like the rovers on Mars, right? This is basically a submarine. And inside this submarine are 5 instruments, a giant sapphire window so we can image the surface, never been done before from descent, and carrying with us analytical chemistry experiments like the ones that have run on Mars on Curiosity for 11 years. We're going to bring the lab to the samples. It's hard to get the samples back, pretty tough. We're going to bring the lab, and we're going to measure stuff that has not been measured before in the history of the, I didn't do it right, in the history of the exploration. And our mission is going to do a lot of things. We have a spacecraft that will fly by Venus twice, making movies of the motions of the clouds as that upper atmosphere super rotates and the ground slowly rotates almost backwards. So we'll measure the clouds and what they're made of. We'll also look at Venus on the night side where it virtually glows to see what some of the large highlands are made of. And then we'll take the plunge. And after we fly this mission in a few years, 0.5 terabyte of data will come back for everyone to figure out our sister. And together with our other missions, our sister missions, we'll get to know it. So let's take a look at what we're going to do. Whoop, I guess I didn't hit it hard enough. One of the things we're going to do is enter the atmosphere in a big 8-foot aeroshell, the kind of thing that brings the astronauts back. But we have to do that at Venus, where we don't know as much about the atmosphere. And then we'll fly on a parachute collecting samples in the deep cloud deck, where some scientists think there could be a cloud biosphere. Now, we don't even know what's there very much, so that question's a tough one. So we're going to measure what's there. We're going to be the chemists to tell those great biologists what to look for. And then we'll come out of the clouds, we'll jettison our big parachute, and then we'll become an imaging chemistry lab, making measurements every couple hundred meters all the way to the surface, into that super dense critical CO2, measuring trace gases, potentially looking at gases that would tell us about astrobiology. Now, so what happens? I got to tell you this story because it's kind of exciting. So we fly around the sun twice, image Venus flying by, it's kind of exciting. And then we arrive at Venus and we take the plunge. We hit the upper atmosphere with 3,000 watts per meter squared energy. That's a lot. The heat shield has to take out all that energy to protect our spacecraft, developed right here in the United States, here in Maryland and Virginia and California and Texas, Arizona, New York, Michigan, to protect those 5 instruments. So we'll come out of that super high Q phase after a few minutes where we won't even have communication. And then, whoop, there we go. And then we'll come out and we'll hit the upper atmosphere and we'll take our first sample. And we have instruments that can measure parts per billion of stuff. That's good. So we can look to see whether the ratio of heavy to light hydrogen in the water vapor that's minuscule up there agrees with what was measured 50 years ago with an instrument that's 10 times better. And then we'll come into the atmosphere and we'll measure, collect samples, and then we'll scrub them and clean them and measure the noble gases. Who doesn't love the nobles? I ask you all. Anyone like the nobles? Well, nobles from helium to xenon are really important because they are the fossil fingerprints of processes that have shaped Venus's atmosphere. We're going to measure them, including those of xenon, which is the heaviest and hardest to partition, to see whether Venus' atmosphere is a new atmosphere. Was it developed by volcanoes, seeded by comets, blown off by impacts? What the heck happened? It's a total mystery lab. So we'll measure that with our instrument developed right here in Maryland, and then we'll come out of the clouds, cut our parachute, and we'll begin imaging for the first time in the history of women and men the surface of Venus in near-infrared windows where we'll see the surface through the dense Rayleigh scattering atmosphere. You might think, it's not going to work. Trust me, it works. And we're going to do that all the way down to the surface, collecting up to for a region that is called Alpha Regio, the first area seen from the Arecibo radio telescope on Venus when it irradiated Venus in the late 60s. This is an area twice the size of Texas, half the size of Australia. We're going to come in over these mountains that rise 10,000 feet above the surface. And we'll start imaging to see what the mountains are made of, what's the relief like, because we can't see this kind of stuff from above the clouds. There's too much stuff in the clouds for us to see. So we're bringing our eyes under the clouds. Makes sense? It's just very hard to do that. So these mountains may be an ancient continent, and they may have clues to, may have clues to, sorry about that, there we go, may have clues to how Venus worked. So as we, up high, we'll collect pairs of images, stack them together, and make topographic maps the way the folks who do the movies do, using structure from motion. Take a lot of little images, stack them up, and make a topographic map. And then we'll do it again and again and again. If we have a good day on Venus, we'll collect 300 images. Not 2, not 3, 300. And by using ratios of the wavelengths of infrared light, we'll see whether the rocks are continental, granites, rhyolites, or other very primitive rocks. They may be sedimentary, like a lot on Mars. We'll be able to tell the difference. And working with our sister missions, understand what that tells us. So we have a lot to do in a mission where most of the action will occur in basically an hour. And as we get close to the surface, our spacecraft will start interacting with the surface chemistry and the minerals. We'll be able to tell what minerals may be reacting. We think they're going to be out of equilibrium. So are they iron sulfates? Are they something else? We don't know. People have seen iron chlorides. And then we'll come down and we'll leave our legacy on Venus. The first time the United States spacecraft will have reached Venus like that since 1978. Where were you all in 1978? A lot of you are young, so you weren't even born yet. So we're going back, 21st century instruments, whole new cadre of women and men to study this world and put it together in a beautiful tapestry, inspired, we think, by Leonardo. From the history of water, whether there were oceans, to indications of volcanism, chemistry, the interactions of the clouds, the whole kabang. This is what we're going to do with Da Vinci in a 2-year mission launching in June 2029 from Florida. Be there. Aloha. I think they say that in Hawaii. Now, I have to finish with reminding you that it's a darn curious universe. We haven't been back to Venus with anything like this literally in almost 50 years. By the time we go, it'll be 53 years. That's a generation. That's how long it's been since we went to the moon with people. We're going back to Venus to take the artistic views of the Venus we don't know and bring the chemical, scientific views of the Venus we can know. And that's going to change everything. The astrobiologists are going to go crazy. We know, looking for what they could find. We'll produce journals like this. These aren't real. These are the faux journals that we are going to write the papers. All of our young teammates, I'm kind of old, so I have lots of smart people running this mission. They're going to do this. Maybe we'll do surfing on Venus if we find the signs of those oceans. And so I like to remind you that this is a very dynamic mission. There's kinetic events, flying through an atmosphere at 20 meters a second, coming down and hitting the surface at 25 miles an hour, collecting almost a gigabit of information never before imaginable for Venus, never before collected for any planet, and taking Venus and putting her into a context that reminds us of the visionaries 500 years ago. This is Florence, of course, where Da Vinci did some of his work. So we have a team across the United States. We're bringing Da Vinci's name with us to Venus to get to know her, and we're very excited. And this is the 100 of us that worked on the multi-steps proposals. It only takes a 1,600-page proposal to be allowed to even enter this playing field. So all these bright women and men did all the work, not me. And we're lucky to get the opportunity to bring us all back to Venus, to put Venus into the context of Mars and Earth, exoplanets we're discovering right now around the TRAPPIST system. It's a great universe. We can't wait to get back. And I'd just like to finish with a little history. 500 years ago, Da Vinci did his thing. He made the first 3D map of a city without an airplane or a drone or anything. It's quite good, by the way. Magellan sailed around the Earth. 500 years later, in the name of those folks, we're going back to bring the legacy of Da Vinci, art, science, everything together, and try to make us part of that story. So thank you all very much, and I'll hand it off to the next speaker.